Hello, in this video we are going to go over interaction of the forces and the system part 2. All right, so starting with friction. Friction is a force that resists the movement between two objects when they make contact. So it resists sliding action between two surfaces, and that can be an internal force or an external force. Like we could have friction between two cartilages inside of a joint or between a ligament and a bone. So we can have internal frictions or intrinsic frictions, and we have friction that is external or extrinsic that's applied to the body from the outside, like the friction between your feet and the ground, just as an example. So a force vector representing friction is parallel to the two sliding surfaces and has an opposite direction of the sliding. Okay, so like in our picture here, if that purple box on top is being pushed towards the right side, friction is an opposite vector that's pointed in the opposite direction of the motion, and that friction is resisting the sliding of that object on top compared to the object on the bottom. Okay, normal force is the portion of the applied force that is vertical or perpendicular to a surface. So it presses the two surfaces together. Which is why friction occurs between the two surfaces. Okay, so the portion of the applied force that is horizontal and parallel to the surfaces making contact is opposed by the equal and opposite force of friction, resulting in forward propulsion during locomotion. Okay, so it's the opposing force to friction that causes us to be able to propel ourselves forward. So it's not the friction itself, but it's the opposing equal and opposite force of friction that causes us to be able to push off of the ground rather than sliding, like if we were trying to walk on ice, where we didn't have that same friction. We wouldn't have that opposing force that would propel us forward when we're walking on ice. Okay, static friction is when we have friction between two surfaces, but at the moment, those surfaces are not moving. So static, like stationary. It occurs between two surfaces that are in contact and have the potential for movement, but are not currently sliding. So when we're going to start pushing something, or something is going to start sliding on another surface, we have to first overcome static friction to be able to initiate that sliding. So it resists the start of an object sliding relative to another, and the amount of static friction depends on the weight of the object and the texture of the surfaces. Okay, so if we're gonna slide a box like this person up in the picture here, there's a big difference between trying to slide it on a wood floor versus sliding it on like a shaggy carpet. There's a huge difference, even though the weight of the box might be the same. But there's a big difference in the texture of the surfaces, so that's going to increase the amount of static friction. And then static friction, we have to overcome, and then once we're in motion, now it's kinetic or dynamic friction. So it's a lot easier, there's less resistance once the objects are already moving compared to having to overcome the static friction in the first place. The coefficient of friction, that's a dimensionless value, somewhere between 0 and 1, that tells us how much friction there is between two surfaces when they are sliding against one another. Okay, so there's no dimension. When we say dimensionless, we mean like there are no units. It's not like this much pressure, that much force. Like there are no units. It's just a number between 0 and 1 that tells us how much friction there is. So 0 would be there's no friction at all. 1 would be there's no movement at all. There's total adhesion, and we can't slide those surfaces relative to one another at all. So this is measured scientifically. So the coefficient of friction has been determined between any combination of many different materials, like we see in the table here. So many coefficient of frictions have been identified between common materials like steel on steel, rubber on concrete, and we can go on, like we see in this table. So in this table, we're seeing the coefficient of frictions in the left or in the center row, in the center column, I should say, those are the coefficient of friction of static friction. And then on the right is of kinetic friction. So as you can see, for static friction, those numbers are all greater than for kinetic friction. So it is harder to overcome the friction when the two materials are not moving. But once they are moving, there is less friction there. And so that's what we're seeing here. So the closer it is to 0, the less friction there is between the two. And the closer it is to 1, the more friction there is between the two. So we could see, like, all the way down at the bottom, synovial joints in humans, 0.01, that's very close to 0, at least on this table in terms of how we're rounding here. That's pretty close to 0. So there's very, very little static friction in synovial joints in humans. And then in kinetic, or once the joints are moving, the kinetic friction is even closer to 0. We get to 0.003 for synovial joints in humans. Compared to others like glass on glass, static friction 0.94, that's very high, and then it drops dramatically once the glass is already moving on the glass. We get to 0.4 for kinetic friction. Okay, so kinetic or dynamic friction is the friction that occurs between two already sliding surfaces. So the coefficient of kinetic friction is less than the coefficient of static friction, like we just saw on the last slide. There's less resistance to sliding between two surfaces that are already sliding. So it's easier to keep something sliding than it is to initiate the sliding in the first place. Rolling friction is another type of kinetic or dynamic friction, but in this case, one surface is rolling over the other instead of sliding. So like tires rolling on the ground when we're driving. So the coefficient of rolling friction is significantly less than that of static or kinetic friction. So like when you're driving, there's a huge difference between driving normally and the tires are rolling on the ground compared to when you slam on your brakes and your tires are skidding on the ground. Huge difference. Obviously, when we slam on the brakes and our tires are skidding, we're doing that because we're trying to produce more friction and stop the motion of the car. Okay, so rolling friction, there's way less resistance to movement than with regular kinetic or dynamic friction, and that's illustrated by the tire movement on the ground. It's much easier to roll an object over a surface than it is to slide in most cases. Okay, fluid forces. Fluids apply two types of forces on a system. So there's dynamic fluid force that is applied to the body when we move through the fluid. And then there's buoyant force that is applied to the body because it's been immersed in the fluid. So we're going to talk about both of these. So buoyant force is a force applied to any object when it's submerged in a fluid, and it's applied in the vertical upward direction. Okay, so when we get into like a swimming pool or bathtub or whatever body of water, we are displacing water when we get into that fluid. So the buoyant force is the force applied to us in the vertical upward direction because we've been submerged in that fluid. And that is because of Archimedes' principle. Okay, so it's the principle that describes the phenomenon and why that happens. So it says that the amount of buoyant force that lifts the submerged body will be equal in magnitude, so equal in amount, to the weight of the displaced fluid. Okay, so if the weight of the body is greater than the weight of the displaced water, then we sink. If the weight of the body is less than the weight of the displaced water, then the body will float. So that's why somebody who's very densely muscular is not going to float very well, and somebody who has more adipose stores, they are going to float better, and that's because of the density of those tissues. So dense muscle is going to weigh more than the water that muscle displaced, and much less dense fat tissue is going to weigh less than the water that it displaced. And of course, it's variable because fat and muscle density can fluctuate depending on the muscle, depending on the person, depending on training and all that. So the density is not set in stone. But generally speaking, muscle is going to be more dense than water and fat is going to be less dense than water. And so that's why those different body types, some people are going to be better able to float and some people are going to be more prone to sinking. That's also why we might float more or less depending on the type of fluid that we're immersed in. Like there's a big difference between swimming in fresh water and swimming in salt water. Okay, so we are more buoyant in salt water because of the weight of the water we're displacing compared to the weight of our bodies that are doing the displacing. Okay, dynamic fluid force is a force that resists movement through a fluid. So like while we're in the water and we're swimming through the water, dynamic fluid force is the force of the water that is resisting our movement. So as the body moves through a fluid, the body is pushing fluid particles aside. So as we're moving, we're contracting muscles that cause our bodies to change in shape. And as we're changing in shape, we're exerting force against each of the little individual particles in the water. Each of those little individual particles are exerting an equal and opposite force against us. Just like when we're walking across the ground and our muscles are changing the shape of the body, so we're exerting a force into the ground and the ground is resisting us with an equal and opposite force, the ground reaction force. And that causes us to move, or causes us to be able to walk or jump or whatever it is we're doing. So in the water, it's the same idea, except the difference is that when we're in the water, we are the thing with a greater amount of mass and therefore a greater amount of inertia compared to each of the little particles in the water. So we are exerting a force against those little particles. They are exerting an equal and opposite force against us. But because those little particles are so much smaller and have less mass and therefore less inertia, they're the ones that move out of the way, as opposed to like when we're walking on the ground, we're the ones with less inertia than the earth. And so we're pushed away from the earth. Okay, so in both cases, the forces are equal and opposite, and it's whichever thing has less mass and therefore less inertia that gets pushed away from the other. So when we're in the water, the little particles in the water have less inertia and they get moved away. Okay, so dynamic fluid force, that is kind of like the ground reaction force, but it's the opposing force of the water particles, the water molecules that are resisting us. And that's the dynamic fluid force. Okay, so that dynamic fluid force, we can break into its component forces, just like we've talked about a lot, where we can take a force and we can find its vertical and horizontal components. So if we take a dynamic fluid force and find its vertical and horizontal components, where if we add them together, we get the resultant force, that's what the drag and lift forces are. So the drag force is the parallel component of dynamic fluid force that acts opposite the motion of the body and resists movement through the fluid. Okay, so the drag force is the force going in the same parallel direction as the movement of the body, but it's going opposite. So it's resisting the motion of the body. The lift force is perpendicular. It's a perpendicular component to the direction of the motion and to the drag force. It's perpendicular to that. And so it acts in a perpendicular direction relative to the direction of the movement through the fluid, and it can cause perpendicular movement in any direction depending on the current motion of the system. So lift force, although it's called lift force, it could have a downward action or an upward action, not only an upward action. It depends on the direction of the force or of the movement. Okay, so if we're moving at an upward angle or moving at a downward angle, that is going to change the direction of the perpendicular components. That's going to change the direction of the lift the lift force to be in an upward or a downward direction. So drag force resists the movement itself. Lift force changes the direction of the movement in the upward or downward direction. So these terms also apply when we're talking about air resistance. So here we're talking about resistance in a fluid, But those terms also apply and operate in the same way when we're talking about air resistance. So we have drag force and lift force. Also, when you talk about like airplanes and things like that. Okay, a motive or a propulsive force. So we can take all the many forces we've described and we can categorize them as being motive or resistive. So is it causing the motion or is it resisting the motion? So a force that leads to a change in motion or acceleration of a motion is a motive or a propulsive force. So an example is if we have a concentric muscle action. So we have a muscle action where the muscle is shortening as it's producing force. That is an example of a motive force. We have a concentric muscle action where the force produced by muscles is sufficient to overcome the resistance to movement, and then motion results. Okay, so we have a concentric muscle action, like in this picture, we have biceps brachii that is shortening and contracting, and it's producing enough force to overcome the resistance of the weight of the forearm and the dumbbell. So in that case, that force produced by biceps brachii is an example of a motive or a propulsive force. A resistive force would be one that tends to prevent a change in motion or that's resisting the motive force. It can prevent a change in motion, or it can decelerate a motion that's already happening. So like for example, in an eccentric muscle action, the force produced by muscles resists the motive force of gravity as an object is lowered. So like if I'm going back down from my bicep curl, now biceps brachii is contracting eccentrically. So it's contracting and producing force as it's lengthening, and it's doing that to resist the motive force of gravity. Okay, so in the extension, gravity is the motive force, because if I produced no muscle force at all, gravity would just go clunk and it would pull down on my forearm and the weight. And so as I'm extending the elbow, biceps brachii is contracting eccentrically to resist that motive force of gravity to control the lowering of my forearm and the weight. So the same force can be motive or resistive depending on other forces acting on the system and the direction of movement. So like the example of biceps brachii, it's the same muscle producing the same force, but when we're going in flexion, it's acting concentrically, and that's the motive force. And when we're extending the elbow, now it's acting eccentrically and acts as a resistive force against gravity. So the force itself didn't change, but what changed is what other forces are acting and the direction of the movement. Okay, centripetal force is often misunderstood. So although centripetal and centrifugal forces are described as being forces, they're actually more like adjectives to describe the effects of other forces. Okay, so there is no just centripetal force like there is friction. Like it's not its own force. It's a term we use to describe the actions of other forces. Okay, so centripetal force is a force that causes a system to move in a circular center-seeking way. So any force that is causing something to move in a circular path, we could say that that force is a centripetal force. And in other cases, that same force might not be causing something to move in a circular way, and in that case, it would not be a centripetal force. Okay, so an example would be like pulling on a rope to cause it to move in a circular direction. It's like if I took a rope and went like this and caused it to move in a circular direction, in that case, my muscle force that is causing my arm to move like this would be acting as a centripetal force on the rope. Another example is gravity causing the moon to move in a circular path. So the moon orbits the Earth because of the Earth's gravitational pull. So in that example, gravity is acting as a centripetal force that keeps the moon orbiting the Earth. Whereas in other scenarios, gravity is not a centripetal force because I'm sitting here on the couch right now because of the effects of gravity, but I'm not moving in a circle. So it's not acting as a centripetal force on me, but it is acting as a centripetal force on the moon. Another example would be friction causing a car to drive in a circle. Okay, so if we're in a car and we're doing donuts in a parking lot or driving in a circle, the friction of the tires, the rolling friction of the tires against the pavement is what is allowing us to drive in a circle. And so in that case, friction would be the centripetal force. But then as soon as we straighten out the steering wheel and go straight, now friction is not being a centripetal force. There's still friction there, but that friction is allowing us to drive in a straight path. So now it's no longer a centripetal force. Centrifugal force is even more confused in terms of how people use the term. It refers to center fleeing, so a force that causes a center fleeing sort of path, so the opposite of centripetal force. The tricky thing is that centrifugal force actually doesn't exist. So like with centripetal, how we would use it as an adjective to describe another force, we couldn't ever call a force centrifugal. There is no force that's acting opposite the centripetal force in terms of like causing motion to be in a center fleeing way. But instead what's happening is there's less centripetal force. Okay, so like imagine we're in the car and we're driving in a circle. And so like I mentioned, friction, rolling friction specifically of the tire against the ground is what is allowing us to drive in a circle. So that's centripetal force. Now let's say we hit a patch of ice. And while we're driving over that patch, we don't have rolling friction, or it's very much less as we drive over that patch of ice. And that causes us to skid off of our path. We're no longer driving in a circle. So there wasn't a force that acted on the car to cause it to not drive in a circle anymore, but instead it was that we had less centripetal force. We had a lack of the friction that was causing us to drive in a circle. We have a lack of that when we hit that ice, and that's what allowed us to jump off our path. Okay, so what we call centrifugal force is really when we have decreasing centripetal force. Okay, so there actually is no opposing force that causes a centripetal force to be reversed. Okay, so it's just less of the centripetal force. Okay, so that is all I have for you in this video, and I'll see you for the next one.